projects. In this video, we are going to explain about the project entitled as Deep and Lightweight Neural Network for Histopathological Image Classification. So before getting into the video, let me give you the brief explanation about the project. This project focuses on accurately analyzing medical tissue images while maintaining low computational complexity. The approach combines deep learning's ability to extract rich, discriminative features with a lightweight architecture suitable for faster training and deployment. This balance enables efficient and reliable classification of histopathological images, supporting early disease detection and clinical decision making. Coming to the abstract emphasizes the importance of histopathological image classification for early disease and cancer diagnosis while addressing the limitations of traditional deep learning models that require high computational resources. It introduced a deep and lightweight neural network designed to achieve high classification accuracy with reduced model complexity and computational cost. By using efficient convolutional operations and optimized feature extraction, the proposed system enables faster and more reliable diagnosis, making it suitable for real-time and resource-constrained medical environments while effectively supporting pathologists in clinical decision making. Coming to the existing system for histopathological image classification mainly uses deep convolutional neural network architectures such as VGG, ResNet, DenseNet, and Inception. These models are effective at learning complex features for medical images and often achieve high classification accuracy. However, their deep and complex structures result in large model size, high memory usage, and long training times require powerful hardware like GPUs. Moreover, these networks are prone to overfitting due to the limited availability of labeled medical data, which affects their ability to generalize well. As a result, despite their strong performance, such models are less practical for real-time use and deployment in resource-constrained clinical environments. Coming to the proposed system or base paper work, the proposed system focuses on designing a deep yet lightweight neural network specifically optimized for histopathological image classification. Unlike traditional heavy models, it employs efficient convolutional operations such as depth-wise separable convolutions and feature reuse mechanisms to significantly reduce the number of parameters and computational cost while preserving classification accuracy. To address the challenge of limited medical data sets, data augmentation and regularization techniques are applied, helping the model generalize better and avoid overfitting. As a result, the system achieves faster training, reduces hardware requirements, and reliable performance, making it well suitable for real-time clinical use and deployment on edge or resource-constrained medical device. Coming to the dataset, the Break His Breast Cancer Histopathological Dataset is a well-known and widely used benchmark dataset for breast cancer image classification. It contains 7,909 RGB histopathological images collected from 82 patients using optical microscopy at 4 different magnification levels, which helps models to learn features at varying scales. The dataset supports both binary classification, like benign versus malignant, and multi-class classification by categorizing tumors into 8 distinct subtitles. Each image is systematically labeled with a class, tumor subtype, magnification factor, and patient ID, ensuring structured and reliable data organization. This comprehensive labeling and diversity make the dataset highly suitable for training, evaluating, and comparing deep and lightweight neural network models in histopathological image classification tasks. Coming to the novelty or extension or enhancement or improvement. As an extension, The YOLO family of models is used to detect and localize abnormal regions in histopathological images, enabling precise identification of suspicious tissues area rather than only performing image level classification. Furthermore, GradCam is employed to generate visual heat maps that highlights the important regions of the image influencing the model's prediction, improving interpretability, transparency, and trust in diagnostic process. And a web-based user interface is developed using the Flask framework, allowing users to upload histopathological images and receive real-time predictions from the trained models, making the system accessible and easy to use for clinical and research applications. Coming to the flow of the work, firstly, we need to import the packages. This step initializes the project by importing all required libraries for deep learning, image processing, data augmentation, model evaluation, YOLO-based detection, and Flask web development. These packages enable efficient data handling, model training, evaluation, and deployment. Next, data preparation. Breast cancer histopathological images are collected at four magnification levels: 40x, 100x, 200x, and 400x to capture both microscopic and structural tissue details. The dataset is organized to support both classification and detection tasks. Next, pre-processing. In pre-processing, we have classification and detection. In pre-processing, we have classification and detection. For classification, image data augmentation techniques such as resizing to 299 into 292, random horizontal and vertical flipping, rotation, and affine transformations are applied. These steps increase data diversity, reduce overfitting, and ensure compatibility with deep learning models with images finally converted into tensor format. And for detection, images from all magnificent levels are merged into a single data set. A data.yaml file is created to define image paths and class labels, enabling proper training for YOLO-based object detection models. Next, maintaining parallel data sets. Two parallel data sets are maintained, one for classification consisting of images and class labels, and another for detection containing images with bounding box annotation. This separate ensures smooth training for both tasks without data conflicts. Next, model training. For classification, multiple baseline classification models including exception, inception v3, VGG16, MobileNet v2, and ShuffleNet are trained on all magnification data. Along with this, a proposed lightweight exception model is trained to achieve high accuracy with reduced computational complexity. Model training for detection. YOLO-based detection models are trained to locate cancerous regions and identify their class within histopathological images. Each model learns spacious and systematic features for precise abnormality detection. Next, model evaluation. Classification models are evaluated using accuracy, precision, recall, FN score, and confusion matrix to measure predictive performance. YOLO detection models are evaluated using MAP, precision, and recall, and their results are compared to identify the best performing version. Coming to the front end application, a Flask based web interface allows users to upload histopathological images for analysis. The backend first performs detection using YOLO model, followed by classification using the best model, and displays the final output as bounding boxes with predicted cancer type and confidence score. The algorithms used are exception, inception v3, VGG16, MobileNet v2, ShuffleNet, lightweight exception. Coming to the extension we used, YOLO v5, YOLO v8, YOLO v9, and YOLO v11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Anaconda, primary language is Python, Front-end framework is Flask. Backend is Jupyter Notebook. Database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder consists of all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And these are the model files which contains algorithm information which will be loaded into the project code during the runtime. All these are IPYNB files. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Next, signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, firstly, copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. By using the command cd followed by a space and then paste the copied path in the Anaconda prompt. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have home button and sign up button. Now, click on sign up button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on sign up so that all the given details are stored in signup.db and the login.html will be open, where we need to access the application by username and password. Then click on login so that the prediction page has been displayed. In this page, we have prediction button, data visualization button, notebooks button, and sign out button. Firstly, click on prediction button. As we are going through classification and detection, we have two different predictions like classification and detection button. So firstly, click on classification button so that the uploading image for classification will be opened where you need to upload the image. Click on browse files, go to the project's code folder. Here we have the test cases. Open that and go to classification and choose any one of that and select the image, click on open and choose the model from where you have chosen. Then click on submit for classification so that the input image is pre-processed and the output is displayed like it is a benign. This is the original image and this is a GradCam visualization image. And here we have about this benign tissue, what this means, and we also have the characteristics and we have the recommendations, safety precautions and next step. We have the upload another image button, view graphs button, and back to home button. If you click on this upload another image button, again it goes to the classification where you need to upload the image and again classify the image. So as we have seen for classification, now let us check for the detection. Now click on detection button so that the uploading image will be opened, where we need to browse the files and upload the image from the test cases of the code folder. Detection. Choose any image, then click on submit for detection. The input image is pre-processed and the detected images has been seen here. Detection analysis is completed. And about the object detection, we have what do you mean by the detection and the detection features. We also have understanding the detection results and recommendations and important notes. Here also we have the same thing like upload another image, try classification, view graphs, and back to home. Now click on data visualization. As we have seen classification and detection, first check the graphs for classification. As we have collected the data for 4 magnification levels like 40x, 100x, 200x, and 400x, let us check one by one magnification classes metrics. First, we have 100x magnification classification metrics graph. In this, the first graph is comparison of metrics across models. This graph compares the performance of different classification models using accuracy, precision, recall, FN score, and error rate. Standard deep models such as exception, inception, VGG16, MobileNet V2, and ShuffleNet shows consistently high performance with low error rates. The lightweight exception model has slightly lower accuracy but demonstrate reasonable performance with higher error rate, highlighting the trade-off between efficiency and accuracy. Next, we have accuracy comparison graph. This graph illustrates the accuracy comparison of different classification models. Exception, Inception, VGG16 and MobileNet V2 achieves very high accuracy, close to 99%. The lightweight exception model shows slightly lower accuracy, indicating a trade-off between model efficiency and performance. Next, precision comparison graph. This graph compares the precision value of different classification models. Exception, Inception, VGG16, MobileNet V2 and ShuffleNet achieves very high precision, indicating fewer false positive predictions. The lightweight exception model shows lower precision, reflecting a trade-off between reduced complexity and predictive accuracy. Next, we have recall comparison graph. This graph shows the recall performance of different classification models. Exception, Inception, MobileNet V2, VGG16 and ShuffleNet achieves high recall, indicating effective detection of positive cancer cases. The lightweight exception model has comparatively low recall, reflecting a balance between reduced model complexity and sensitivity. Next, we have FN score comparison graph. This graph compares the FN scores of different classification models. Exception, Inception, VGG16, MobileNet V2 and ShuffleNet achieves higher FN scores, showing a strong balance between precision and recall. The lightweight exception models has a slightly lower FN score, indicating a trade-off between model efficiency and overall classification performance. And next we have error rate comparison graph. This graph illustrates the error rate comparison across different classification models. Lightweight exception shows a higher error rate compared to the other models. Exception, Inception, VGG16, MobileNet V2 and ShuffleNet achieves very low error rates, indicating more accurate prediction. Next, we have 200x magnification classification metrics. The first one is comparison of metrics across model graph. This bar chart compares 6 models across 5 metrics like accuracy, precision, recall, FN score and error rate. Exception achieves the highest score overall with the lowest error rate, while lightweight exception and ShuffleNet have slightly lower performance. All models shows consistently high performance with minimal difference in metrics except for error rate. Next, we have accuracy comparison graph. This graph compares the accuracy of 6 different deep learning models. All models shows very high accuracy, close to 100%, with only small difference between them. Exception Inception VGG16 and MobileNet V2 perform slightly better than Lightweight Exception and ShuffleNet. Next, we have Precision Comparison Graph. This graph shows the precision values of different deep learning models. Exception VGG16, Inception and MobileNet V2 achieves very higher and similar precision scores. Lightweight Exception and ShuffleNet have comparatively low precision than the other models. Next, we have Recall Comparison Graph. This graph compares the recall performance of different deep learning models. Exception shows the highest recall, while lightweight exception has the lowest. The remaining models achieve similar recall values with only minor difference. Next, we have F1 score comparison graph. This graph compares F1 score of 6 deep learning models using a horizontal bar chart. All models achieve higher performance with F1 scores roughly between 0.93 and 0.99. Inception, Exception and VGG16 shows the highest F1 scores while lightweight exception is slightly lower. Next, we have error rate comparison graph. This graph compares the error rate of 6 different deep learning models. Exception shows the lowest error rate while lightweight exception has the highest. Overall, the most models exhibit low error rates, indicating strong classification performance. Next, we have 40x magnification classification metrics. First, we have the comparison of metrics across the models. This graph compares accuracy, precision, recall, F1 score, and error rate across 6 models. Exception and VGG16 shows the strongest overall performance with very high scores and minimal error rates. Lightweight Exception and ShuffleNet perform slightly lower with comparatively higher error rates. Next, we have accuracy comparison graph. This bar graph compares the accuracy of 6 deep learning models. VGG16 and Exception shows the highest accuracy, close to 100%. Lightweight Exception has the lowest accuracy, while the other perform similarly well. Next, we have precision comparison graph. This graph compares the precision of different deep learning models. Exception and VGG16 achieves the highest precision values among the models. Lightweight Exception shows the lowest precision, while the other perform consistently well. Next, we have recall comparison. The graph shows the comparison of recall values across deep learning models. VGG16 and Exception achieve the highest recall, indicating strong detection capability. Lightweight Exception has the lowest recall, while the remaining models show similar performance. Next, we have F1 score graph. This graph compares the F1 scores of 6 deep learning models. Exception, Inception, VGG16 and MobileNet V2 achieves the higher performance with F1 scores close to 1.0%. Lightweight Exception and ShuffleNet perform slightly lower but still show strong results. Next, we have error rate comparison graph. This graph compares the error rate of 6 different deep learning models. Exception and VGG16 shows the lowest error rates, indicating better performance. Lightweight Exception has the highest error rate, while the other falls in the moderate range. Now we have 400x magnification classification metrics graph. First, we have comparison of metrics across the model graph. This graph compares accuracy, precision, recall, F1 score, and error rate across different deep learning models. Exception, Inception, and VGG16 achieve the best overall performance with higher scores and low error rates. Lightweight Exception and ShuffleNet have shown comparatively lower performance and higher error rates. Next, we have accuracy comparison graph. This bar chart compares the accuracy of different deep learning models. Exception, Inception, and VGG16 shows the highest accuracies, all around 95 to 97 percentage. Lightweight Exception has the lowest accuracy, while MobileNet V2 and ShuffleNet perform slightly below the top models. Next, we have precision comparison graph. This graph compares the precision of different deep learning models. Exception achieves the highest precision, followed closely by Inception and VGG16. Lightweight exception has the lowest precision, while MobileNet V2 and ShuffleNet show moderate performance. Next, we have recall comparison graph. This graph compares the recall values of different deep learning models. Exception and Inception achieves the highest recall, indicating strong ability to detect true positives. Lightweight exception has the lowest recall, while MobileNet V2, VGG16 and ShuffleNet show moderate performance. Next, we have F1 score comparison graph. This graph compares F1 scores of different deep learning models. Exception and Inception achieves the highest F1 score, close to 0.98%. Lightweight exception has the lowest performance, while others show strong similar results. Next, we have error rate comparison graph. This graph compares error rate across different deep learning models. Exception has the lowest error rate, indicating the best performance. Lightweight exception shows the highest error rate, while other models fall in between. As we have seen the classification graphs, now let us check the detection graphs. First, we have YOLO precision graph. The graph compares the precision of different YOLO models like V5, V8, V9 and V11. YOLO V5 shows the highest precision, closely followed by YOLO V8 and YOLO V9. YOLO V11 has slightly lower precision compared to others. Overall, all models demonstrate relatively similar precision performance. Next, we have YOLO recall graph. The bar chart compares the recall performance of different YOLO models. YOLO V9 shows the highest recall, followed closely by YOLO V8 and YOLO V5. YOLO V11 has the lowest recall among the models shown. And next we have MAP score graph. The bar chart compares the MAP performance of different YOLO models. YOLO V9 achieves the highest MAP, closely followed by YOLO V8 and YOLO V5. YOLO V11 shows slightly lower MAP compared to the other models. And then click on sign out. So finally, the proposed deep and lightweight neural network efficiently balances high classification accuracy with low computational complexity of histopathological image analysis. The model demonstrates strong generalization while significantly reducing parameters and interface time. This makes it well suited for real-time and resource-constrained clinical environments, supporting reliable and efficient disease diagnosis. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.